Chapter 2, Atoms and Elements. If you cut a piece of graphite, so let's imagine you break the tip of your pencil, right? That happens all the time. And you take that piece and you cut that piece in half, and you take one of those and you cut it in half. How far could you go? Could you divide it forever, or would you eventually come to a smallest particle? It's a rhetorical question. You don't need to answer that. Eventually, and this would be cutting it far smaller than you could see, so you couldn't actually do this, you would end up with individual carbon atoms. So this would be a little like taking a big Lego structure, right, and karate chopping it in half, right, and taking that half and cutting it in half and cutting it in half. Not using tools or anything else, but just your hands. Eventually, you're going to get down to individual Lego bricks, and you can't divide them any farther, right? That's how matter is. You can cut it and break it down, but eventually you're going to get down to atoms, and you can't go any smaller than that. So the word atom comes from the Greek word atomos, meaning indivisible. You can't divide the carbon atom into smaller pieces and still have carbon. If we want to understand matter, the world around us, we have to understand atoms. So that's where we're starting with this chapter. Okay, Brownian motion. We're going to have some history in this chapter. I am not going to test you on history. There will be no dates and mostly no names at all. Any names would be associated with a particular law or something, but not in terms of history. So 1827, Robert Brown was looking through a microscope at water-suspended particles that had come from pollen grains. So pollen grains floating on water, and he's looking at them with a microscope, and he sees there's actually smaller pieces that are coming off of these grains of pollen. And I've got a video here. It's obviously not a video of his work in 1827, but it's the same sort of thing he was looking at. So let's look at this. Oops. It's Tuesday, but it's acting like Monday. So these are the grains of pollen, these big pieces here, and these are the particles coming off. So there's jiggling, right? Very short movie. So Brown observed this motion. He wasn't wiggling the microscope or anything. It was just sitting there. But the particles are wiggling. What's going on with this? He initially thought that the particles might be alive, you know, small little organisms, right? And they jitter around. But he finally concluded that the source of the motion was not coming from the particles themselves. In 1905, this is a while later, Albert Einstein developed a theory about this. That motion was called Brownian motion because Robert Brown was the one who discovered it. He explained that this Brownian motion seen in these tiny particles is a result of water molecules banging into them. And so they're suspended in the water. The water molecules, which are too small to see in the microscope, are banging into these particles, and that's causing them to jiggle around. It's a bit like a beach ball thrown into a crowd, right? The beach ball comes on, people hit at it, right? And it just jumps around because people are hitting it. These particles were wiggling around because the molecules of water were hitting them, okay? This was probably the first substantial evidence for the existence of atoms and molecules. The existence could be inferred from Brownian motion. Does it prove anything? No, but this work by Einstein and other people following removed any doubt about the particulate nature of matter. Before this, people, they believed that it was particulate, but nobody really had any proof or really any evidence. So that was significant. Fast forward to the 1980s, a couple of researchers at IBM in Switzerland developed what's known as a scanning tunneling microscope, or STM. The basic idea here is that there's a very sharp needle, metal needle that comes to a fine point, really one atom at the tip. And we have a surface that we're going to be looking at, and they apply an electric voltage between this tip and the surface. And when the tip is close, an electric current will flow. It'll jump from one surface to the other through the air. The amount of that current varies with how far away the tip of the needle is. So you can hold the distance constant by monitoring the current and having the computer move that tip so that the current is always constant. So they take this tip and they move it back and forth. It's called rastering. In a zigzag pattern, they scan it back and forth, maintaining that current. So basically the tip's coming across, and when there's a bump on the surface, it lifts up, and then it'll go back down. And if there's a bigger bump, it'll lift. So it's kind of like a topographical sort of mapping. It doesn't give us a visual image directly, but we can take the computer signals and create a visual image with them. And we can see images like this. These are the Japanese kanji characters for the word atom, written with iron atoms, those are the reddish purple ones, on a copper surface. That's the blue that we see. The colors are just from the computer so that we can see what's going on here. And so that the tip of that microscope comes across and it lifts up and over and up, and it jiggles around. Atoms are not cone-shaped like that, but that is an artifact of how they're detected, that it comes up, and it can't really detect a perfect, the sphere that's sitting there. We just see the overall surface. So how do you get individual atoms to be characters, or how do you move them at all, one at a time, when they're too small to see? So here's another little YouTube clip showing how that can be done.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on the surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Any questions? Is that kind of cool? Yeah. So you can imagine the amount of time that went into making this one image. That's not a fast process to go in there and pick up an atom and move it over and drop it. It's going to be quite tedious. But it's mind-boggling that it can be done. So, you know, scientists, we may be nerds, but we like to have fun as well. And so these scientists at IBM made a movie using this technique, basically a stop-motion animation. It's called The World's Smallest Movie. So let's watch that. So there's another video that shows how they made it, and it's very interesting, but I don't think it's worth class time to show in class. But I have put all these videos that are in the lecture also separately on the YouTube playlist if you want to watch them or show somebody because you thought it was cool. You think about it, that movie, that is the ultimately small pixel, isn't it? You can't get smaller than an atom. So those are the smallest possible pixels. To help us get an idea of how tiny that is, so we're going to think about the Library of Congress. So the Library of Congress in Washington, D.C., they've got all the books, right? All the books. They have 35 million books. And if you put them on shelves, it takes 840 miles of shelving. So that's a lot of books. If you took all the words in all of those books and wrote them using letters the size of the kanji characters on the previous slide, they would fit in an area of 5 millimeters square. Teeny tiny. What? Right? I mean, talk about compact storage, right? Wow. Now, you'd need a scanning tunneling microscope to read it, so that would be a bit tedious. But this is an interesting element of science of making things smaller and smaller and smaller. And there is a limit to how small things can get, but it's pretty mind-bogglingly small. The atoms, so small, but they are the key to explaining the large things that we can see. An atom is the smallest identifiable unit of an element. There are smaller particles than atoms, but they are not identifiable as belonging to a particular element. So in terms of elements, there are 91 elements that occur naturally, and there are over 20 synthetic elements. Those have been made in a lab. They do not naturally occur in nature. On the periodic table up here on the wall, the elements with white letters, they're just an outline, those are all man-made elements. Okay? So you see that The naturally occurring go up to 92, but then there's also element number 43, which is not naturally occurring, technetium. So that's where the 91 naturally occurring elements come from.